Okay. So, hello everyone. Last time we started to discuss penalty methods. The plan for today is to finish them and then continue with barrier methods. And on Thursday, we will see how to use these ideas in semi-definite programming and convex programming. Sorry, quadratic programming. So let's quickly review what we discussed last time. So you remember our goal is to minimize a function f over a set S. And we denote this problem with P as our primal problem. And to solve this, we introduce a penalty function P, which had these properties that P is continuous, it's non-negative, and it is 0 if and only if X is in our constraint set S. So when we are in S, we don't penalize. Otherwise, we penalize the function f with c times px. So special case is when the set is defined, the constraint set is defined with these inequalities. And the useful penalty function in this case is the, say, the sum of the quadratic of the positive parts of these GI constraint functions. We also discussed this figure here, which just shows that if we increase C more and more, then the penalty is higher and higher if we are outside of our constraint set S. We had 4 lemmas that we proved. So first we defined this function Q as function f of x plus c times px. And the penalty program was this, that at iteration k, xk is the argmin of q ckx, where this ck is just the increasing number of positive parameters, and they diverge to infinity. And last time we proved these 4 inequalities, that function q is increasing, the penalty is decreasing, the function value is increasing, and as we do more and more iterations, this function q can be sandwiched between the optimum x star and xk, the function value at xk. So as we go from step k to step k plus 1, this function value will be increasing, and we will converge to this function value f of x star. We proved this 4 lemmas last time. And we also proved this penalty, the convergence of the penalty method theorem, that if f and g, f, g, p, they are continuous functions, xk is defined as we just discussed, and c are increasing positive numbers diverging to infinity. And if x bar is any limit point of this series that our algorithm generates, then this limit point will solve the primal problem. And we proved this theorem. We discussed a couple of important penalty functions, such as polynomial, linear, and quadratic. And we also discussed what we should do if instead of inequalities in our constraint set, we have equalities as well. And we discussed that in that case, one thing we can do that so far, this was our penalty function, and we just add this term as well. And this is where we stopped last time. Any question about anything? Everything is simple, easy? Good. Good. So let's continue here. So we had our original constraint function f. We modified that with the penalty function. So our new constraint is f of x plus ck times px, and we want to minimize this. But now it's an unconstrained problem. X is in the n-dimensional Euclidean space. F and p, they are continuous smooth functions, so we can calculate their derivatives. Oh, sorry, so f is continuous and g is continuous, and we want to calculate the derivative of this function. So the problem here is that px was defined as a function gamma of the positive part of these functions g. So g plus ix was defined last time as the maximum of 0 and g ix. And we want to calculate the derivative of this with respect to x. That's a bit problematic, right? Because the maximum function is not continuous, right? So, but the idea is that, frankly speaking, we don't need the derivative of this g plus. We need the derivative of this px. And if gamma function is chosen in the right way, that in that case, even though this g plus is not a continuous function, gamma g plus can be a smooth function, and we can calculate its derivative, right? So that's what we are going to do now, right?
Why do you say it's not continuous?
Oh, I meant sorry, right? So at 0, it jumps, right?
Not smooth.
Not smooth, yeah. So. Right, you are right. So, sorry. So, at 0, it's not smooth, right? So, if it's negative, it's 0, and then it's the identity. Any other part where I confused you more? Okay, but the rest is true. Okay, so our plan is to choose a gamma function in such a way that this p will be differentiable. Okay, so we need to calculate the derivative of the penalty function p. And if we just do the calculation, we have m constraints function. Maybe let me come back to this previous slide. So you should remember these definitions, how g plus was defined. So this is g plus I, the maximum of 0 and g I x. And g plus x is an m-dimensional vector. Its components are g1 plus and so on, gm x. And px, the penalty function, is defined as gamma function of g plus x, where gamma maps an m-dimensional vector to positive numbers. So if we use these definitions, so for example, one gamma function could be that gamma y is just y transpose y, where y is an m-dimensional vector. So if we use these definitions, then the derivative of p with respect to x is So remember, Px was gamma j plus x. Where gamma maps m-dimensional component y to real numbers, right? So this is real. So because of this, I have to take the derivative of gamma with respect to its I coordinate at where? G plus x. And I have to multiply this with gi, the I coordinate, with respect to dx. But again, the only problem is this guy here, that what should be him? Right? It's just calculus. So how should we define this expression? Gi plus x dx. So what is this? So if Gix is negative, then what is this expression? So if Gix is negative, right? Okay, and what is this expression if Gix is positive? So we take derivative with respect to x, not with respect to Gix. Right, so it's the derivative of Gix if Gix is positive, right? But again, the problem that with this that this might be not continuous in 0, right? Because it's 0 here, but if it's Gix is positive, then it might jump to this value. Okay, so the solution is that we define function gamma such a way that if yi is 0, which is right, gi plus x in our case, then the derivative of gamma y will be 0. In that case, it doesn't matter if this guy is not continuous here, because I will multiply it with 0. Right? So in that case, this px function is differentiable. Okay, so an example where this gamma function has this property is you can easily check is this function. Oops. The polynomial function. For some q bigger than 1. Right? So if you take the derivative of this, then even though this guy would be not continuous, it doesn't matter because this first term would set that to 0. So now how this function looks like is that, say this is Gix and say dpx over dx. So the derivative of px is, as we discussed here, is sum from 1 to m is delta gamma over delta yi multiplied by this delta gi plus over dx. And now say this is 0. If gix is negative, then this term here will be 0. However, if gix is positive, then it will be smoothly increasing. Okay? So the lesson is that even though this maximum is not differentiable, we can still choose a gamma function. It's very simple calculus that makes this px differentiable. And then we are good. Right? Mm-hmm. Yi. So gamma was a function that maps an m-dimensional vector to real numbers. It's say maps a vector y to real numbers. Its I coordinate is yi. And so how would you calculate the derivative of this px over x? So you have to sum over all components of this function gamma. It has m components. That's why from sum 1 to m. And you have to take the derivative of gamma with respect to each component. I just use the notation that the derivative of gamma with respect to the ith components is d gamma over dyi. But where do we calculate this derivative? In g plus x, right? And then we need to multiply this with the derivative of gi plus x over x. Is it clear now? Right? This is just the chain rule. Okay. So let's see how to use these functions in the Karush-Kuhn-Tucker with the Karush-Kuhn-Tucker conditions. So our penalty program is this, as we discussed, and we choose the penalty function to be gamma g plus x. And now we know that the gradient of px is, we have m constraints. So yi, and if you want, I could write this way too, that delta yi over delta x, where this yi is gi plus x. So an other thing we have to notice is that, so I could just write this, that this is delta gi plus x over dx, where this is defined by this, that this is the derivative of gix if gix is non-negative and 0 otherwise, right?
Technically, it's at 0, it's any number between.
It
At 0, it will be any number between 0 and.
you
If it's strictly positive, it's that. If it's negative, it's the other one. But if it's equal to 0, then it's
so which function you are talking about?
subgradient.
Right. So I
It's a technical.
yeah. So it could be anything there. You are right. In our case, it doesn't matter because with this gamma function, we cancel those turns out, right? And here the point I want to make is that this should be the derivative of gi plus x. But do we need this plus here? We don't, because what is this guy? It's the derivative of gi x if gi x is positive, and 0 otherwise if gi x is negative. But when gi x is negative, we choose the gamma function such a way that this will be 0 in that case. So I could just write this, that the derivative of px is this expression multiplied by with the derivative of gix over x.
That's 0 only when it's at 0. Not less.
Right. But at g plus, right? So you still evaluated g plus. So you are right. It's would be 0 only at that point, but we are evaluating it in that point. Other questions? So it's good now, right? I mean, other than that, it can be defined anyway.
No. So I mean that this is the gradient when it's larger than 0.
Right.
And when it's smaller than 0, it's 0, right? And
Right.
the gradient of
But then this expression here will be 0.
Right.
Right. So my point is that I can write the derivative of px in this form. That this expression multiplies by the derivative of gix over gx. That's all. Okay, so our goal is to minimize this function, and we already know the derivative of px. So what's the first order condition in a local minimum? Is that its derivative is 0. So at xk, the derivative of f at xk plus ck derivative of p xk, that's 0. And we just calculated this expression. Which is, I just repeat to be clear that this is xk. That this is this expression. Okay, so if you look at this, if I rewrite this as u, say I at iteration k, then what we have is that this is gradient of f of xk. Oops, I want to include in uik the ck term as well. So let me write this way. So what this form remind you? How does it look like? Like this uik term. So where did you see something like this, that the derivative of function multiplied with something and the derivative of another function? What? I cannot hear. So, oh, okay. So just name one. So okay. So what I want to here that they are look like Lagrange multipliers, right? Although the derivation was completely different, right? And so we introduced penalty functions, calculated its derivative, and we got this form. We could have done the other way too, that we have the function, introduced Lagrange multipliers, got something else at the optimum, right? So at the optimum, if you use Lagrange multipliers, we would have, say, some u star here at the optimum. And now you might wonder, if we increase k, so as we proceed, whether this guy will converge to the Lagrange multiplier or not. So in the limit, as we do this iteration, whether this expression will be that one that you would have got from just using Lagrange multipliers. Is it clear what I'm wondering now? Right, and there's a theorem which says that under very mild conditions, it's indeed the case. So if you introduce these uik numbers, then they will indeed converge to the Lagrange multipliers at the optimum at x star, right? So if, yes? So I defined uik this way. And you can prove that if, say, xk converges to x star, the optimum, then this uik will converge to u star, where u star would be the Lagrange multiplier at the optimum x star. So it's just the connection between Lagrange multipliers and penalty methods. At the limit, they are the same. In the limit, they are the same. Okay. So I hope that after this, you can use penalty methods and you can build algorithms. If you see a function that's continuous and differentiable and you have some constraints set, then you might be able to introduce a penalty function for that. And if you can take the derivative of the penalty function, then hopefully you can find local optimums. Okay, so there would be many interesting ways how to proceed this analysis, like how to do after that gradient descent, Newton method, conjugate gradient, and so on. But let's move on and let's discuss barrier methods. Unless you have any questions with penalty methods. Yes?
So for different CK, you find different penalty. So it's different optimization problems. So does all of these problems solve independently, or will CK influence the solution for CK?
Right. So we had a theorem that no matter how you choose this series CK, if it diverges, then your penalty method will converge to the solution of your original program, right?
Yeah, yes. But if I choose CK, the initial value of CK is very, very large. So
Oh, that's a technical issue, that if your initial value of CK is large, then it might be difficult to solve that problem. So that's why. Right, so so you choose a huge CK and you want to use Newton method, it might be not stable enough. So in Newton method, when you need to invert the matrix, it might be difficult to do that. So that's why what people do is that they choose a small CK values, you do a minimization, have your optimum, and from that optimum, you do you increase CK plus 1, and from that starting point, you solve that new optimization problem, and hopefully that will be easier than if you just initially choose a big CK.
Local minimum, not global minimum. First order condition.
Right, yes.
Why it is local minimum?
Oh, why?
Why it is local minimum, not global minimum?
So So I mean, it's just a general statement that we had this function here, right? And it might be not convex, right? The minimum, how to find its one of its local minimum, is that you check when its derivative is 0.
fx might not be convex.
Right, so it's
Maybe the solution maybe also a local maximum.
right. So there are many different cases. One is that so what we discussed here, we have never said that f should be convex. Okay, so that's why we are just talking about local optimum points here.
Is there a result known about what if you don't solve xk exactly? Like, I mean, you're going to use, to solve this sub-problem, you're going to use Newton or the gradient or anything like that. And you're going to get it's an iterative algorithm with an approximate solution. So you're never really going to get argmin x. You're going to get argmin x with some error.
Right.
How do these errors propagate? Like, is there something that as long as you solve xk to a smaller and smaller accuracy at every iteration, then you will still get
Right. So there are rates, there are results on that too. That it's not necessary to solve these precisely these problems.
But I'm not sure why you're saying the errors propagate if they don't, because you're not using xk across iterations. That you're just changing the sequence.
Right, but I thought your question is whether I need to solve these.
Unless I'm doing something different, like I'm using them some other way. I might just have some constant edit, but it won't kind of propagate out.
Right. That's true.
Right, so we have many other things to discuss today. So let's move on. If you have more questions, use my office hours, please. That's always a good place to ask questions. So penalty methods, I hope they are now they are clear. So another important family is called barrier methods. Our problem is the same. We want to minimize a function f over a set S, where f is continuous and S is the constraint set again. And again, we don't say that we don't require f to be convex at this point. The barrier program is similarly to the penalty program. We will replace this original problem with another problem, which will have this form, that we want to minimize the same function f of x again, plus constant time the barrier function, where this constant will be always positive, and the barrier function will have these properties that this is continuous, and it's non-negative for all interior points in the set S. So in the interior points of set S. And as we move towards the boundary of set S, this function will diverge to infinity. So in other ways, we start our optimization inside the set S. It might be not optimal, but we have a feasible point. And we don't let the algorithm to go out of set S. Okay, so for example, if the set S is represented with inequalities, a trivial example is if, say, g1x is x minus b, g2x is a minus x, it means that our set S is those points x that are between a and b. And a useful barrier function could be minus the sum of 1 over gix. So gix is negative inside the set S, minus 1 over gix is positive, and you can see if I'm somewhere, so this is set S, if x is going to point A, then the barrier function 1 over gix would diverge to infinity, and the same thing would happen if we converge to point B, right?
What if the optimal solution is actually unbounded? So then we maximize the L2 norm and unconstrained the circle. Actually, we get the optimal solution unbounded.
Right. It's a good point, and let me come back to this question later. We will see what happens. We will solve linear programs, and then you might ask the same question. Okay? So for now, let's just to simplify your life, let's assume that the solution is inside the boundary, and then we will discuss later what we can do if it's not the case. Okay? So let's have a few minutes break now, and we continue from here. So the barrier program will be defined like this, that for a C parameter, we want to minimize f of x plus 1 over c bx, where b is the barrier function. And we will do the same thing as we did with penalty method, that this c will diverge to infinity. We start with a small c, which hopefully makes the problem, this barrier program, easy to solve, and then we increase c. If c would be infinity, then this problem would be equivalent with the original program. That's difficult to solve, right? But so the idea is the same as with the penalty methods. Another important barrier function is the logarithmic barrier function. So if our constraint set is represented again with these functions, that gix is non-negative, then the logarithmic barrier function is defined as minus some the logarithm of minus gix. Okay, so if x is feasible, then gix is negative, minus gix is positive, so the logarithm will be positive. And as we approach 0 with gix, then this expression would diverge to infinity. Right? And the barrier method, similarly to the penalty methods, we start with some non-negative C1, and we have a C2 that's bigger than C1, and so on, and ck plus 1 is bigger than ck, and it's diverging to infinity. And the barrier problem with parameter ck is defined as xk is the Argmin. We are in the inside of set S, function f of x plus 1 over ck, the barrier function at x. Because I'm too lazy to write, I will just denote this 1 over ck with mu k. So ck is diverging to infinity, so this mu k will converge to 0. And now you might say we didn't do much, because this barrier problem with parameter c is still a constraint problem, right? Because we say that x is in the interior of S. And now it even looks more complicated than the original problem. But the good thing with this barrier problem is that because of the nature of the barrier function, we can solve this barrier problem with unconstrained optimization tools. That's the whole idea here. Okay. So again, let C1, C2 be increasing positive numbers. The barrier program with parameter ck is xk is the minimum point of f of xk plus 1 over ck b xk. And then we have the same for lemmas that we had with the penalty functions. They have the same flavor, but they look a bit different. So with penalty functions, we denoted this f of x plus constant times penalty with function q. We denote this with function r, ck, xk. And we have the following 4 lemmas. You remember what was the relation between these functions when we discussed penalty functions? So I'm just wondering whether you can guess what the relation will be here. Anyone brave enough to guess? Yeah. So like this? This or the opposite? Okay, I will leave it here like this. Let's see. Second try. So what happens with the barrier function values? This? Okay. How about here? F of xk. Oops. Right. So if you remember with penalty function, it was not like this, right? But here, k plus xk plus 1 is smaller than f of xk. And we also have this that at x star, oops, right? So what happens here is as we increase k, then we converge to x. We will converge to x star, and the function values will be decreasing and converge to x star. So it's the opposite than what happened to the penalty function. Okay, so we have these 4 lemmas. The proofs are very similar to the proofs what we discussed with the penalty functions. So I would skip them, but it's a good practice for you to do it. You can never know if one of them might be in your midterm questions, for example. Okay?
How is B increasing?
Why this is true?
Yeah.
So you really want to see the proof, right?
No, it's only Q.
So how about this, that the calculations will be in the slides. I don't want to discuss them now. If you have questions, then come to my office hours if you don't understand the proof from the slides. But it's really the same as we had with penalty functions. And again, I want someone to come to my office hour. Please. Okay, so if you are interested, it's here. So write proof 1, proof 2, proof 3, proof 4. Very simple. Okay, but let's just move on for now. If we have time, we can come back to discuss them later. But I want to discuss how to use them. And the first algorithm I want to discuss is how to use logarithmic barrier functions to solve linear programs. So the primary problem is that I want to minimize C transpose X over X subject to, say, AX equals B and X is non-negative. So this is the standard form of linear programs. So please help me. What would be a good log barrier problem here? So I want to minimize f of x, where what would be a good f of x? I start. You continue. So you are hesitating. Why? It's too easy or too difficult? Or okay, I continue. Minus me sum. So what we have two constraints, right? X is non-negative and AX equals B. So let's put a log barrier function on X is non-negative first. X is in the n-dimensional space. Right. This is inequality constraint, right? The X is non-negative.
Like AX equals.
Right, that's equality constraint, and that makes you hesitating, right? And that's the thing that with barrier functions, if you have equality constraint, you might not use barrier function for that term. So we just leave it there. We just use barrier function for x, okay? So we want to minimize this f of x subject to ax equals b. So, but indeed, I could have started from that linear program where, say, ax is smaller than or equal to b, and then you could put a barrier function on these constraints as well. But let's just ignore this for now. If we have time, we come back to this later. So this is our function f. We want to minimize this. And we do the same thing as we did before, that we calculate its derivative. So it's gx. Let gx denote the derivative of f of x. Can you help me what that is? So what's the derivative of f of x with respect to x? C minus mu so what's the derivative of this guy? Right. So let me just write this way, that dx will be a diagonal of matrix made of vector x, and this is the inverse of that. And let me multiply this with E, where E is this 1, 1, 1, 1 vector. Okay. And I'm just curious, what would be the second derivative of function f? So what's the derivative of g of x? What? I cannot hear. So what's the derivative of? Right. Right, so this is a matrix. Very good. So now we can use this, and you can use Newton method, for example, to minimize this if you want. Okay. Oh yeah, I still have the constraint, right? So we need, right, for example, projective Newton method. So let's see a few more details, and we see how to handle that. So the idea is that we start from, say, x bar, which is a feasible solution. Solution to this barrier problem with parameter mu, right? So this is b mu. And we start from this, and in the next step of the iteration, say, we move to x plus, where x plus is x bar plus some delta x. We want to minimize this function f. It looks a bit ugly, but what we can do is that the usual trick, that we approximate this with the quadratic function, right? So we have this function f. We want to minimize this subject to these constraints. First, let's just approximate this function x. So if we use second order Taylor approximation, then this would be f at x bar plus the gradient x bar transpose x minus x bar plus x minus x bar, the second derivative of f of x bar times x minus x bar. Where did I make a mistake? Someone? Yeah, so 1/2, right? And we just calculated this, that this is this function gx, and we calculated the second derivative. Oops, gx bar, gx bar. right? So what we are going to do that we minimize this quadratic function where we have these constraints that Ax equals B. Okay, so we want to minimize. So let me just denote this quadratic function with Q delta x, where this is delta x, x minus x bar. Oops, Q delta x. Right, so our goal now is to minimize this quadratic function subject to A. We move to this new point from x bar plus delta x, and we have this constraint, right? And at x bar, we also know that A x bar is beta. So from this, it follows that A delta x is 0, right? This is our constraint. So we have a quadratic function, which is a function of delta x. We have this linear constraint. So what can we do? We use Lagrange multipliers. So if I denote the multipliers with pi x, then we had the derivative at x bar transpose delta x plus 1/2 delta x transposed gx bar, the second derivative, times delta x. And now minus the Lagrange multiplier pi x transposed my constraints A delta x. So what do we need to do? We need to calculate the derivative of this Lagrange multiplier with respect to delta x and pi of x. And we solve that equation, what we have. Right? It's very simple because it's just linear in delta x and it's linear in the Lagrange multiplier pi of x. Right? So just to repeat this quickly. So this is the Lagrange function. In the optimum, we have that the derivative of the Lagrange function so what's that? The derivative of this is gx bar. And the derivative of this is a linear function. What will be the derivative? Gx bar multiplied with delta x, right? And the derivative of this with respect to delta x is A transposed, very good, pi of x. So we know that this is 0. And we already calculated this expression and this expression. If you remember, this was C minus mu dx inverse E. You calculated this, and you also calculated this, which was mu dx to the power of -2. And now what we have is that it's just a linear system that mu, so from this mu dx to the -2 and A transposed multiplied with minus delta x and pi of x. That's this expression here, C minus mu dx inverse E. And we also had another constraint, that is A delta x, that was 0, right? We had this constraint here. So I write that here. This way. So from the Lagrange function, we got the first row of this equation, and from the other constraint that A times delta x is 0, we got the second row. This is a linear equation. We just need to solve this for delta x and pi of x. So you solve this for delta x, everything you know, and that will be your update. So x plus will be the previous x bar plus delta x. So this algorithm is called primal log barrier method for linear programs. Any question with this? What we did? So just to summarize, we had linear cost function. The constraints were that A times x equals b, and x is non-negative. For x is non-negative, we used the trivial barrier function. We had a new nonlinear function. We approximated with second order Taylor approximation, and we solved that using the other constraints that A times x is b. And we calculated, we solved this as a Lagrange problem, and this whole problem reduces to this linear system. So if we had a feasible point x bar, we can update with this delta x that we calculate from this linear system, and you can repeat this process. Okay, so you have a new point x plus, and then in the next step, you can reduce your mu because you want to converge to 0, and then you redo this whole thing. You calculate these new parameters, solve the system again, and hopefully that works. It's called primal because we just use the primal problem. But I hope we have still some time. Yes. So there's a primal dual method as well, where we use, again, our goal is to solve linear programs, and we will use both the primal and dual form for that. Any question? Very simple, right? Yes?
So we had an equality constraint to start off with. Suppose if we split that into two inequality constraints, ax less than b and x greater than b, put barriers on each of them, we still recover.
Right, so that could work. The only difficulty is that you should be able to start from a feasible point that's inside. Right, so, Oh, yeah, that's true, right. So what you can do, is that if you have that ax equals b, is that quite often you can rewrite that problem that ax is less than b, and you can use barrier function for that. So as you remember, for linear programs, we had many equivalent forms. And for some of them, so let's discuss that with more detail. So what we solve now is that was C transpose X minus mu right, and our constraints were that AX equals B. But quite often your linear program has this form that AX is smaller than B. And sometimes they also have that X, here we also had that X is non-negative, right? Sometimes people also have that, say X is non-negative. And now if you think that you could just rewrite this, that AX plus some slack variables equals to B, where X is non-negative, S is non-negative. And then this problem would be equivalent to the first one, right? So instead of doing this, you can use this barrier function, that is C transpose X minus, say, mu times BI. So BI is the ith element, and AI is the ith row of A. Right? So in this case, this problem would be equivalent to that problem that I just erased. And still for this, you can use this barrier function. Clear? Good? Question?
I think again, as long as the AX less than equal to B does not have, I mean, you could have constraints like minus x1 minus x2 less than equal to 2, and x1 minus x2 less than equal to minus 2, greater than equal to minus 2, whatever, that kind of x1 plus x2 less than equal to 2.
So
you can implicitly encode
right, so the assumption is here that you have to start from an interior point of this, right? If you don't have that, then of course you are in trouble. But if you have a interior point to start this algorithm, then it's good for you. Right, but it's same with any linear programs. It might happen that you don't even have any feasible point of that, right?
In linear programs, you'll have feasible points to satisfy that, but you need a strictly feasible point, AX less than B, to run.
Right.
Like linear programs, you can still solve if AX is less than equal to B, that is, you can find points, some of which are less than and some of which are equal to. But for this, you need that everything is strictly less than. To start off with, you have a point that AX less than B.
Right, you have to start with that. That's, yeah, true. What I wanted to say is just that there are linear programs where you don't even have feasible points. Okay. Right, so in this case, if you use this form, then this is what would happen. So say in this case we have 2 variables and 6 constraints. You can see these 6 constraints as the size of this polytope. And let me denote this function with phi. These dashed lines are the contours of the levels of this function phi of x. And for each mu, say for mu equals 10, we solve this problem. In the solution, the gradient of C transpose X should be parallel to the gradient of this phi of X. So the gradient of C transpose X, you see, is this vector. So it means that in the optimum solution, this line should touch this dashed line here, right? So the gradient of C transpose X, that is vector C, should be parallel in the optimum with the gradient of this. In other words, I can just say that they are in the optimum, this dashed line touches this contour here. And if you increase mu, say this is, I don't know, 5, then this would be your new solution. And as you decrease mu to 0, then finally you would converge to the optimum solution X star. And you can see that here the solution happens in the corner. It's not in an interior point. Still, we can use these interior point methods to converge to a corner point, because for each mu positive number, the optimal solution of this f of x will be inside. But still, using this interior series of interior points, we converge to the global optimum in this case. This line here, so x star mu, where mu is the parameter, that's called central path. And it's also clear, right, why it's called interior point methods, because we are inside of the feasible set and we converge to the global optimum. So next time we continue from here.